Alrighties. Hello, Year 12s. Welcome to your second lesson for physics. We are starting the course proper. So we're looking first of all at motion in one dimension, which is projectile motion, as we discussed. Most of the stuff will be things you already know. There shouldn't be anything new in terms of context, maybe some new content, maybe some new phrases, but should all be stuff you've already seen before. So first and foremost, kinematics or kinematics. We use it to predict the future position of an object. To predict the future position of an object, we need to know if it's already moving, where it is, so its position, and how long it takes to move, the time. The quantities that we're interested in is how quickly it moves, so velocity, and how quickly it changes velocity, which is acceleration. We also need to be aware of a frame of reference. So a person moving on a train at one velocity with respect to passengers and a different velocity with respect to the ground. So if you have the train, it's going, the person is walking, it's moving at one velocity to the people in the train as opposed to when it's looking at it compared to the ground. If someone is walking in a train at 2 meters per second in the train, and the train is moving at 30 meters per second, in the train, the person will be moving at 2 meters per second with respect to the people in the train. With respect to the ground, it will be moving at the speed of the train plus their own speed. Okay? And there's an example right there. So a person moves at 5 kilometers per hour in the direction of the train's motion. The train moves at 80 kilometers per hour with respect to the ground. The person moves at 85 kilometers per hour with respect to the ground. And the Earth provides a useful fixed reference frame. But even the Earth is moving relative to the Sun and stars, so we tend to just disregard that unless we're doing things that involve gravity or space. Alright, so displacement in one dimension. So displacement is the difference between the current position and the starting position. Like I explained to the year 11s, displacement doesn't care about the in-between space you move, it just wants to know how far you are from where you started to your current point in time. So for example, a person walks 70 meters to the east, turns around and walks 30 meters back west. Total distance traveled is a 70 plus a 30, which is 100 meters of distance. Total displacement, 70 in a positive direction, 30 in a negative direction, gives you 40 positive G's. When you're doing your displacement, when you're writing vectors, do not forget to write its direction. Vectors have direction, always. They're magnitude and direction. Two things you always need to write with vectors. And direction can either be east, west, north, south, or things like positive and negative, or minus and plus, depending on the context and what the vector is you're using. Please do not forget that. So once again, quantities with the direction and magnitude are called vectors. Quantities with only magnitude are scalars. Okay? So average velocity. Average velocity is defined as a change in displacement divided by the time elapsed. So velocity, not speed, using vectors, therefore we're using displacement as opposed to distance. So average velocity is displacement over time elapsed. Velocity is also a vector, has direction as well as magnitude. Example, I walk 100 meters west and then 50 meters east, taking 200 seconds. What is my average velocity? What is my average speed? You have two different things. So if we want to work out average velocity, so I'm just going to write this and then show you. Velocity equals displacement over time. A displacement is equal to negative 100 plus 50, because putting west is a negative way and then east is a positive way. That's negative 50, and time is 200 seconds, so our velocity is negative 50 over 200. Is that, you calculate it. Once again, my calculator zero button doesn't work, so I will work it out. It's just going to look really weird because the zero button, once again, does not work. So, 51 take 1, negative 51 plus 1 close bracket divided by that is a minus sign, divided by 211 minus 11 close bracket gives us negative 0.25. There's negative 0.25 meters per second. You can either just leave it at negative 0.25 or at 0.25 meters per second west. Do not forget your units, do not forget your direction, especially when you are working with vector quantities. Alright, if we want to do our average speed, sorry, there it is, the working out on the piece of paper. Okay? If we are looking for speed, we do speed equals distance over time. Our distance is equal to 100 plus 50 is 150. So our speed equals 150 divided by 200, which is 151 take 1 close bracket divided by bracket 211 minus 11 close bracket, which equals to 0.75 meters per second. Okay? There's a difference depending on whether you're talking about velocity, speed. Right. So next, instantaneous velocity. So when the time interval, so delta t, goes to 0, we have an instantaneous velocity as given by the formula. The limit of t going to 0 is delta x over delta t. X is distance or displacement. This is the velocity that the object is traveling at in an instant. So notion, so bold-faced symbol indicates vector, arrow above or squiggly below used to write the vector symbol by hand. So when you're typing on the computer, sometimes you can't put the little arrow on top like we do here. It's a little hard to do, so they put the unit in bold instead. Okay? Alright, so on this graph that we have here, we have the time across the bottom, velocity going up, and then the average velocity as a dotted line through the middle, which you can calculate. Okay, and make sure when you're drawing your graphs, time is always on the bottom, velocity or speed is always on the y-axis, and you write what your units are. See, this is in kilometers per hour, and this is in hours down here. Please make sure you label your graphs correctly. Alright, next. Instantaneous speed versus average speed. So instantaneous speed is what you see in your speedometer. I'm assuming you guys all have your license or have at least driven a car, preferably with your license or on your L's. Okay, so implicitly there is a delta t, but it is very, very small. Okay, to the point where it's basically negligible. A speeder does not tell you your direction; it just tells you your speed. Okay, that's why it is a speedometer, not a velocidometer. The average speed is the total distance traveled divided by the duration of a trip. Okay, so for example, the old trick question, if you travel 100 kilometers at 50 kilometers an hour for the first 50 kilometers, how fast must you do the last 50 kilometers to average 100 kilometers per hour? Alright, next, calculating total displacement. Total displacement is equal to velocity times by time spent traveling at that velocity. So total displacement is the area under the graph of a velocity versus time graph. This is a little annoying to calculate. I need to double check if it's still part of the syllabus, but I'm pretty sure it is. Learning how to calculate displacement based off a velocity time graph like this. Okay, so yes, you can draw a nice square and then count how many squares there are. Well, is this squares? No, 1, 2, 3, 4, 5, 6, 7, 8. Why is it 9? Oh, because it's the area. Alright, that is a typo. That should be 8 meters. That should be 8 meters. Okay. So it's the same way you would calculate any other area of a shape. Alright, so to calculate displacement, total displacement is velocity multiplied by time spent traveling at the velocity. If you know a series of instantaneous velocities, multiply each one by the time spent at that velocity. Out of the displacement for each velocity, total displacement is the area under the graph of velocity versus time. So you have something like this, which looks like a plane, but you can break it down. This is a triangle, this is a square, this is another triangle, triangle, square, triangle. And I'm sure you all remember your year 7, 8 area maths. Shouldn't have to go through that with you. If you're unsure, please double check the formulas online, or if you have your old math textbook there. But basically, you just use them, you add them all together, and you get the area under the graph here. Okay? So, sometimes velocity is negative. That means the direction of travel has reversed. So you started going one way, and then you've done a U-E, and you're going the opposite direction. That means the area below the time axis needs to be treated as negative. So if you're adding these two displacements together, this is a positive displacement, this is a negative displacement, you add them together to get your total displacement. Okay? So going through that. The starting point may also not be 0. So instead of starting at 0, we start at displacement of 0. The area under the graph is the same as before. The graph V versus T doesn't change. This graph here is, the same as this graph here. Okay? And represents the change in displacement. Okay? Next. Average acceleration. Acceleration tells us how quickly the velocity changes. Acceleration is the change of initial velocity over a time interval. So we have average acceleration is equal to change in velocity divided by time elapsed. A equals delta V over delta T. That should be on your formula sheet. Okay, so units of length divided by time divided again by time. This is why we have meters per second squared. Okay, because it is a vector divided by time, despite the fact that, I'm not going to go into that. Not going to go into that. Right. So acceleration has a direction and is thus a vector. In this example, the acceleration is constant and to the right. That is my right, that's your right. To the right. In this example, we have done that. In equal time intervals, the velocity increases by equal amounts. Okay, so we have acceleration. Acceleration is held here. At t, it's going, going. Speeding up. We have a constant acceleration. Okay. So next we have deceleration. Acceleration don't just cause the velocity to increase. Deceleration is when the velocity of an object is increased in magnitude. So if acceleration and velocity are in the opposite direction, the acceleration is a deceleration. Acceleration is negative here because we chose negative to mean to the left. To the left. Okay. So T1 is 0 and V1 is 15 meters per second, and acceleration is negative 2 meters per second squared. In 5 seconds time, we get 5 seconds later, velocity is now 10 meters per second squared because you slow down from the deceleration. These don't feel like real words. I digress. Alright, so continuing with acceleration, a stationary object can have a non-zero acceleration. For example, acceleration, initially deceleration, remains constant. The car comes to rest and then starts accelerating backwards. The car is stationary only for an instant. So basically it's moving, it comes to a brief stop and then starts moving back in the opposite direction. Alright. Plotting this one, properties. So one useful way to visualize the acceleration of an object is to plot a velocity against a time graph. You should have done this in year 11. You should all know how to do these. Okay? Consider the equation for velocity with constant acceleration. This one here. This one here is your best friend. One of the ones that are your best friends. Remember, in physics, formula are your best friends. Do not forget that. Okay? So you have your velocity in meters per second. They have the unit plus the symbol against time, symbol, unit. Okay? So at these points here, well, they've numbered 3 points. 1, 2, 3, and then 3 other points. Sorry. The line segments have been numbered and the points have been lettered. Okay? So we can calculate how fast the object was moving at these different points and anywhere along this line using the gradient. Okay, so to plot it, velocity increased by 15 meters per second in 15 seconds. So from here to here, from the origin to 15 seconds under time, we know that the velocity is increased by 15 meters, has increased, increased by 15 meters per second, increased 15 meters per second in 15 seconds. Okay, you can read that off the graph very easily. Velocity changes 0 meters per second, so it's held constant in 5 seconds, between 15 seconds and 20 seconds, 5 seconds different. No change in acceleration, velocity doesn't change, it is held constant. The velocity decreases by 10 meters per second, so drops from here down to here, so from 15 meters per second down to 5 meters per second. Okay, in 5 seconds, we have 20 seconds, 25 seconds. We can calculate the deceleration, which gives us negative 2 meters per second squared. Okay, and then the acceleration drops to 0 again as it holds as it stays constant at 5 meters per second here. That one's off to the graph. Okay, handy. Constant acceleration. So kinematic equations in 1D motion. Right, action derivations are, that is a textbook we do not have. Alright, final velocity from initial and acceleration. T is time elapsed, same as delta t used earlier. They mean the same thing in this case. This equation is straightforward to understand. Right here. You can rearrange this to get this. Okay? This is just the definition of acceleration. Acceleration is the change in velocity divided by time, or the change in time. Okay? You should all know how to rearrange equations to get them to look how you need them. Sometimes that means if you have to write the numbers in, because that's easier for your brain, go for it. But when I am marking your test, I should be able to trace the logical progression of you using the original formula and then translating it to something like this. Okay? Right. So, kinematic equations, you should have seen all of these before. Learned them first in year 11. So, velocity from initial velocity and acceleration and time. Here. Average velocity from initial and final velocities. You should know how to do this. Average velocity, final, take initial, divided by 2, get average. Actually, that should be right time. I don't know why it's 2 there. Alright, displacement from acceleration. They use an x for displacement instead of an s. Don't ask me why. I apologize, but if you see an x anywhere in these PowerPoints, it is referring to displacement or distance. If it's in bold, it's displacement. If it's just a regular, it's distance. So displacement from acceleration, initial velocity, and initial displacement. Alright, velocity from initial velocity and change in displacement. Let's see. Displacement doesn't have to be x, it could be y, as we will see. We'll get to that a little later. Alright, so constant acceleration, as an example of constant acceleration, is acceleration due to gravity. In projectile motion, 99% of it, we assume that gravity is 9.8 meters per second squared. Okay? We're assuming everything happens on Earth. The only time this changes for us during our course is when we look at gravitational pulls and the force of gravity on different planets. We'll get to that later though. That's like in 4 weeks from now. Okay? So 9.8 meters per second squared is large for an acceleration, and few cars could match it. Also, sometimes you'll see them use this, g equals 9.8 meters per second squared. That g is just the specific acceleration on Earth. Okay? We are going to skip that. Alright, so gravity in different reference frames. So often you can greatly simplify problems just by picking a convenient origin and orientation for your reference frame. If y positive corresponds to up, then the gravitational acceleration is down and negative. We did this a little bit last week when we went into some projectile motion questions to deal with angles and something flying through the air, making an arch and coming back down, and the acceleration was negative because it is coming back down, as the gravity is pulling the object back down to Earth. But the y-axis doesn't have to be positive going upwards. We're going to ignore this part here because this is, once again, uni level stuff. This is what we stick with in high school. Negative 9.8 meters per second squared. Okay. So we have acceleration due to gravity this here, and dropping things at different heights and seeing how long it takes and whatnot. In this case, they did the gravity as a positive because, they're testing that to see how long it takes for it to drop. Alright, if you're throwing something in the air, first of all, we neglect air resistance. Do not worry about it. And then we have your classic questions. If the object leaves the hand at 20 meters a second, how high does it go and how long is it in the air? Qualitatively, what happens is as the ball goes up, gravity acts against the velocity, slows it down, and it drops the ball back to zero. Oh, sorry. It's at A, it comes up. At zero, at B, the velocity is zero because the speed it goes up and the gravitational force are equal to each other and becomes zero, and then it drops back down because gravity is acting on it. And then it's caught back at its origin. Okay. So choose a reference frame with y positive with y 0 as 0 equals a. This means that the acceleration due to gravity is negative 9.8. Velocities are defined as positive upwards and negative downwards, so how high would it go and how long is the ball in the air? You can figure this out using the equations that we looked further back at. Okay, so Mythbusters, I will link this episode on Daymap so you guys can watch it and you can make your own decision about that. Alright, last one. Non-constant acceleration. The acceleration profile for a car is a classic example of variable location. It is not nice and neat. It is often quite messy looking at acceleration, especially if you're driving manual. So note the non-linear velocity time curve. So at first gear, you start up, you're going at one speed, then you shift into second gear and you go a little faster. Third gear, faster again. Fourth gear, faster. And fifth gear is where it caps off at. Okay? That is non-constant acceleration, and I believe that is where we are going to end it for today. All right, see ya!